If you think about earthquake, tsunami, or even just a very loud music concert, then you know that there is energy in waves. If you create a wave, for example, a wave on a string, you need to apply a force to the wave medium. And you know that in mechanics, if you have a force and you have motion, then you have work, and work is energy. In this video, we will show that the power, which is the energy transmitted per second, can be calculated from the tension of the string, the slope of the string, and the particle velocity. You already know from mechanics that the power is equal to the force multiplied by the velocity. And we already learned that the particle velocity is equal to dy dt. So all we need to show is that the force Fy is equal to minus t multiplied by dy dx. The first thing to realize is that the energy in a string can take two forms. The first one is kinetic energy. Since the particles are moving, there is kinetic energy. And the second one is potential energy. Since the string is deformed, there is potential energy. The string can be stretched or compressed, and this will contain the potential energy. And so to model this, I will draw a set of springs. And let's consider the forces on a particle of the string. When there is no wave on this string, the forces of tension are the same on both sides. So the particle does not accelerate. Now let's say that a wave pulse is coming from the left. The particle on the left is moving up, so it has kinetic energy, but the string is going to deform, and part of the energy will transform into potential energy. But now there is a small force on the particle that will make the particle accelerate upward. Part of the energy will be transformed into kinetic energy again. So this will reduce the deformation on the left, so less potential energy on the left. But at the same time, it will increase the deformation on the right, so the potential energy will increase on the right. And in turn, this will accelerate the particle of the string on the right. And so this is how the pulse will propagate from left to right on the string. The energy continuously changes between potential and kinetic. Now let's look at the local slope of the string. It makes an angle theta with the horizontal. And remember that tangent theta is equal to the length of the opposite side divided by the length of the adjacent side. So we can see that tangent theta is equal to minus Fy divided by the tension T. At the same time, tangent theta is equal to the slope of the string, which is dy divided by dx. Right? Because it's a function of x and t, we use partial derivatives, so partial y versus partial x. And combining the two relations, we see that the vertical the vertical force Fy will be equal to minus t times dy dx. And this is what we wanted to show. So we arrive at this relation for the power on a string. Note that this represents the local power transmission because it depends on the particular position x of the string. And this relation is interesting because it also gives the direction of propagation, right? If the power p is positive, then the energy propagates in the plus x direction. And if the power p is negative, then the energy propagates in the minus x direction. Now let's do an example of application of this formula. Let's calculate the power for a sinusoidal wave. Now remember that a wave function for a sinusoidal wave can be written as y, the displacement, is equal to the amplitude a times cosine kx minus omega t. And so a is the amplitude, k is the wave number, and omega is the angular frequency. Now, of course, depending on the initial conditions, it could be a sine function, or in general, we could have a phase shift phi so that we would have kx minus omega t plus phi. And also know that if the wave propagates in the minus x direction, then I would have kx plus omega t. instead of kx minus omega t. So here I'm just choosing a particular example. I'm choosing this wave function a cosine kx minus omega t. To calculate the power using the formula, I'm going to need the slope dy dx and the particle velocity dy dt. So let's calculate those derivatives. For the slope, the derivative of cosines gives me minus sine. So I have minus ka sine kx minus omega t. And for the particle velocity, I have minus sine, but I also have minus omega. So I get plus omega a sine kx minus omega t. And now I can combine this, and I obtain that the power is equal to t k omega a squared multiplied by sine squared of kx minus omega t. You can see that all those terms are positive, so the energy is transmitted in the plus x direction. And I let you check for yourselves that if the wave propagates in the minus x direction, so I have I have a cosine kx plus omega t, then you will obtain a negative sign for the power because the energy would propagate in the minus x direction as well. Also note that the power is proportional to the square of the amplitude, right? You have a square here, which is something that we will see again for other types of one-dimensional waves. Now, this relation contains both k and omega, and this is not very convenient to have both of them in the same relation for the power because k and omega are not independent, right? Last time we learned that k and omega are related by the wave speed, and we have the wave speed v is equal to omega over k. So I can replace k by omega over v. And we also know from last time that the wave speed is given by the square root of the tension divided by the mass per unit length mu. So I can replace the square root and I can replace k by omega square root of mu over t. Now I obtain this new relation for the power, which now depends on omega squared. Still, this relation gives the power at a particular position x and particular instant t, right? And because it varies with time, it can be convenient and can be better sometimes to express some quantities that do not depend on time, right? Quantities that are time independent. For example, we can calculate the maximum power, P max, right? This will happen when the sine function is equal to 1. So P max is equal to square root of mu t omega square a squared. Another quantity that does not depend on time is the average power, right? And this can be obtained if you remember that the average of the sine function of the sine square function over a full cycle is simply equal to 1/2, right? So the average power becomes 1/2 square root of mu t omega squared a squared. And note that this is the same formula as in the LibreText, except that the tension of the string is represented by the letter F in your LibreText, and the angular frequency omega is written as 2 pi f.